Simple probabilities, section 1.1. The goal for this section is to use probability to measure and calculate the likelihood of something occurring. So let's start with what is probability. Well, probability is the likelihood or chance of something happening. So likelihood or chance of something happening. So think of like an event. If it's might rain tomorrow. So what's the likelihood or chance of it raining tomorrow? That you can use probability to describe. Okay. How's probability measured? Well, we measure it using numbers, in particular a value that is between 0. Okay, and when we say 0, it means it's impossible. There's a 0 chance of it of raining dogs and cats from the sky tomorrow. It's impossible. And 1. And if you say the probability is 1, that means it is certain to happen. Okay, you have like 100% chance that you're going to eat tomorrow. That's a probability we can say is measured by saying 1. There's a 100% chance. Okay. 3 types of probability. Subjective probability. And this is probability, a probability estimate based on intuition. Based on intuition, meaning this is based on your gut feeling. Okay, so here's an example. So use subjective probability to estimate the probability of each of the following scenarios. So if we look at the first scenario, A, an expansion baseball team will win the World Series in its first season of existence. Okay, so what's the likelihood of that happening? Well, you see, I think it's very unlikely because it's a new team. So I'm going to write here, it is very unlikely. And on the left side, I left some space here. So I'm going to say, let's give this a 10% chance. So maybe 0.10, which is a number between 0 and 1, which is also the same thing as saying 10%. Okay, so it is very unlikely for a new team. This is a new team. For a new team to win. It usually takes several years for them to contend, meaning it takes them several years for them to be good enough or experienced enough to be a good opponent, a good match. Okay. Part B. The next pair of shoes you will buy will be the same size as the last pair you bought. So I'm going to give this a higher number, something closer to 1. So I'm going to say 0.9, which is 90%. And the reason why it's not 100% is because maybe in this situation you're still growing. So your feet size, your shoe size might be a little bit bigger than your old pair. But for most people, at some point in their lives, the shoe size stays the same. And so you could say that with almost an 100% certainty, or we're going to say here 90%, that the next pair of shoes that either me or you buy will be the same size as the old one. So I'm going to say here, although your foot size may not change. So even if it does not change, well, why isn't it still 100%? Well, there's also other possibilities too. Different brands have different shoe sizes, slightly different. So maybe one brand will do a size 8 shoe a little bit slightly different than the other one. Maybe they'll make it a little bit wider, a little bit longer. Okay, so Although your foot size may not change, shoe size could also depend on style. So shoe size could depend on style slash the brand. Okay. And C, the next person to enter a coffee shop will be wearing jeans. Well, let's give this 0.75, so 75% chance. And the reason why is because jeans, they're very common. So jeans are a common clothes item. Okay, meaning many people wear jeans, and so it's a good chance that it might be true. It might happen. Okay, so let's move on to the next kind of probability, experimental probability, and this is what we're going to define as the observed probability based on experimental trials. Okay. So consider this. How can we find the probability of rolling a 5 on one six-sided die after 10 rolls of the die? Okay. So you're going to roll the dice 10 times. This is an experiment. Okay. So we're going to define what the experiment is. And it's called a well-defined process from which observations are made. Okay, and then so you run your experiment. It's a process that you create. Okay, and you run that experiment, and we're gonna say, okay, what's a trial then? Well, a trial is just one round of this experiment. So a trial is one round of the experiment. Outcome. Okay, so you conduct the trial. Well, then what happens? Well, you measure an outcome. So an outcome is a possible result of an experiment. So if you're rolling a die and you roll a 1, well, that's a result. If you roll a 3, that's a result. Okay? And then we come to, so when I say it's a result, it's an outcome. So this is the formal word we're using we're going to use as outcome. All right? So, rolling a 5 is an outcome of rolling a die in my experiment. Okay? And then we have the final term we need here for experimental probability, and that is event. An event is the outcome that we hope to get. Okay, that you hope to get. So if you're rolling a die, and let's say they said you're going to win $10 if you roll a 5. So the outcomes are 1, 2, 3, and 4, and 5, but the event that we want, that we hope to get, is that rolling of a 5. Okay. Now we have a formula that will help us calculate the probability of an event, an experimental probability, and this formula is P of A. So think of like function notations. P stands for probability, A is my event, and it's equal to the number of times that the event happened divided by the total number of trials. Okay, so it's important to just note here that A represents my event. So the event could be rolling a 5 on a 6-sided die. Okay. All right, so here's an example. Determine the experimental probability of a baseball player who makes 10 hits in 35 times at bat. Okay, so what's the experiment? Well, the experiment is going to bat. Oh, what was I going to say? Going to bat the baseball. Okay, to hit the baseball. So how many trials? So the trial is actually taking going to the bat and making a swing, right? So how many trials did this baseball player do? Well, he did 35 trials. So the number of trials is equal to 35. Now, what's the event? Well, A is uh, the hitting, making a hit. A is a hit. So if you hit the ball, that's an event. What's the other possibility? The other outcome is not hitting the ball. So you miss. So we want to know is what's the probability, or how many times did he hit the ball? So n of A is n of how many times he hit the ball, which is 15, which is 10. 10. Okay. So then the probability that we're going to calculate is the probability that the baseball player makes a hit. And that's equal to the number of times he hit the ball over the total number of trials, which is 10 out of 35. And if you convert that to a decimal, you get 0.286. And as a percentage, that can be expressed as 28.6%. And all you have to do is move the decimal place 1, 2 times to the right to get your percentage. Okay? Or you can multiply by 100. Now, I did all this work here showing you a simple probability calculation. All you need to do as students is simply, I'm just going to highlight here what you need to show. Just show me this calculation here. Whoops, so it's going to have to highlight my yellow color. Let's try that one. So just show me that the probability of an event is equal to what the event is over the total number of trials, and give me your answers. Okay. Now it's useful to actually define these things too that I have here on the left. What is your event in the beginning, just so you know that you know what you're doing. But over time, as you get really comfortable with it, then you can simply skip over to the answers and the formula. Okay, so let's move on to the next thing. Sum of probabilities. So if you add all probabilities in an experiment, the total will always be 1. Okay, so the probability of rolling a 6-sided die, so the probability of rolling a 1, rolling a 2, rolling a 3, rolling a 4, rolling a 5, rolling a 6, all of them will add up to 1 or 100%. Okay, and so that's there in that formula in the red box. So here's an example. One colored chip is randomly drawn from a bag containing a red, a blue, and a green chip. The result is recorded and the chip is replaced into the bag. Find the experimental probability of drawing a red chip if, after 40 trials, the probability of drawing a blue and a green chip are 39 and 24%. Okay, so here I'm going to say that the probability of a red chip plus the probability of getting a blue chip plus the probability of getting a green chip, all of them have to add up to 100%, or 1. Okay. So we don't know the probability of getting a red chip just yet, but we know the probability of getting a blue chip is 0.24 or 24%, plus the probability of getting a green chip is 0.39 or 39%, and that's going to equal to 1. Okay, remember it has to be 1. You can't go over 100%. There's no way you can say there's a 224% chance of getting a red, green, or blue ball. No, it adds up to 100%. Okay, so the probability of getting a red ball is equal to 1. Solving this equation, so 1 minus 0.24 minus 0.39. Okay, and the result for that is, let me just say here, is 0.37. Okay, or 37% chance. So with problems in this course, you're going to have to give me final statements. So I'm going to say here, therefore, there is a 37% chance of drawing a red. Okay, applying experimental probability to predict future outcomes. So probability is a useful tool for making predictions. Although predictions may not always be perfectly correct, they can be close enough to help with decision making. So here's some more examples. A manufacturing process rejects a batch of items if more than 1.5% of items are found defective. If a batch of 400 were to be tested, how many could be defective before the batch would be rejected? Okay, so probability of a reject, so let's say the event is rejecting a batch, is 0.015. How many trials were conducted? So we conducted 400 batch tests. So the number of trials, n of t, is equal to 400. What are we solving for? N of a, the number of trials in our event. Okay, so the probability of event A happening is equal to the number of events, number of times that the event occurred, divided by the total number of trials. Okay, and simply put, the probability is 0.015. 0.015 came from the 1.5% converted to a decimal, which is 0.015. And so I'm going to say here 0.015 is n of a divided by 400. And if I rearranged for n of a, so the number of events this occurred, so 0.015 times 400, which is 6. Okay, so what does this mean? It means, therefore, 6 items can be defective before the batch is rejected. Okay, and this is like a common problem in manufacturing that you'll see, especially if you take something like manufacturing engineering, or you work in manufacturing in general. You know, think of a candy bar. You know, not all candy bars are made perfectly. Maybe there's a misprint on the labeling. Maybe the not enough chocolate in the candy bar. So some of these candy bars get rejected. You know, you notice when you go in the store, the candy bar always looks perfect because they do a lot of quality testing. You know, they check the batches to make sure items are not defective. And if they do find more than a certain number defective, then they reject the whole batch. So here in this question, you know, you're testing batches of 400. Well, how many of those 400 have to be rejected before they reject the entire thing? So that answer is 6. So if 6 of the items out of the 400 are defective, then they are going to reject the whole batch. Okay. Part B. Scientists want to determine the number of deer living in an area of northern Ontario. They catch and tag 300 deer and release them. Over the next year, 125 deer are caught, and 15 of those deer have tags. Estimate the number of deer in the area. Okay, so here we have another problem. So the probability of A, which is my event that I'm going to consider here, so P of A is going to equal what? Well, we're considering here over the next year, 125 deer are caught, and 15 of those deer have tags. So the event is, when we conduct our trial, which getting a deer with a tag on it, that's our favorable outcome. That is our event. So we want to know how many times this event occurred. It occurred 15 times in our experiment, and our experiment conducted a total of 125 trials, meaning we caught 125 deer. So that is the probability of P of A. Okay. Now, N of A. How many deer are tagged in total? Well, 300. Okay, so there's 300 of them. What about uh, n of t? Now remember, this is, I'm going to calculate two probabilities here. So this first one is just kind of what we'll call the local the local probability, just based on this small sample of 125 deer that we've caught. But we're interested in estimating the number of deer in the entire area of northern Ontario. Okay, so there's going to be well over many more than 300 because they only caught 300 deer and tagged them in the beginning. So we're interested in finding that total number in the area. So we're going to use another probability calculation, and we're going to say P of A is equal to the total number of deer that are tagged divided by the total number of deer in the area. Okay, so that's what we're going to try and figure out, n of t. So here I'm going to say 15 over 125, that probability for our small sample of 125 deer. That probability we can use to estimate the probability of all the deer in the area. Set up a simple ratio. And I already know that n of a is 300, so I'm just going to replace that with 300. I'm going to replace n of t with the variable x. Okay, I'm going to say here x is the number of deer in the area. Okay, so x times 15 is equal to 125 times 300. And so if I solve for x, x is equal to 125 times 300 over 15. And that gives me an answer of 2,500. Okay, so therefore, there are 2,500 deer in the area. Okay, so you got to think about this in a more broader context. So it's like, yeah, there is a ton of deer in an area. There's thousands of deer in the area, 2,500. So one day they tagged 300 of them. So they have them tagged electronically. They can monitor. They've tracked them basically. So they tagged them, they released them, and then over the year they looked at catching deer. So they caught 125 deer. They found 15 of those were tagged, and the rest were not. Okay, so how come the rest were not? Well, because the population of the entire area is not 300; it is actually way more. So they use that probability. Okay, so 15 of the 125, and they can use that to estimate the total number of deer. Okay, so if you know you tagged 300 of them, then the total number would be x, and x is what we're solving for. Okay. Theoretical probability now. So theoretical probability, this is defined as the probability based on possible outcomes. I'm going to capitalize possible. So possible outcomes. Given that all outcomes are equally likely, meaning they're fair. They're all fair outcomes. What's a fair outcome? Think of tossing a coin, right? So tossing a coin, fair outcome. Because the coin has the same size on both sides. The weight is just evenly distributed. Okay, same thing with the dice. 6-sided dice have the same size on every side. It's not like one square is bigger than the other. Okay, think of things that are fair. All right. What would be not fair? Well, think of throwing darts at a dartboard. What happens if your dartboard looked like this? So I mean, right now, two sides would be fair, it's the same size. But what if I divided it like this? 1, 2, and 3. Well, obviously, there's a higher chance to hit the side with a 3 on it than it would be with a 1 or 2. That would be unfair. Okay, so theoretical probability, we're going to study outcomes based that the outcomes are equally likely and they are fair. Okay, and we're going to study more of that on tomorrow.